plus 2Na plus NR. And so for a constant volume, the moles of the species are going to be equal to the concentrations. So then you can rewrite, so if you assume constant B, and it says this is a batch reactor, so that's a pretty safe assumption. You can rewrite this as Cb equals Ca naught plus 2Ca plus Cr.
Would that be negative Na naught? Because you have Na naught minus 2 Na naught.
Yeah. My bad. Alright, and so now that you know concentration of Cb, you can go back to this form up here, start solving for the concentration change of A, which is what it originally asked in the question. So go ahead. Erase this. So the concentration of B is 2Ca plus Cr minus C naught. And then, so from part C, you solve for the concentration of R in terms of concentration of A. So then you can plug that in. And even if you didn't get this far in part C, it gave you the equation, so you can just go ahead and solve and plug it back in anyway. And then from here, all you had to do was just plug back in that y equals equal to Ca over Ca naught. And this is what the final question asked. So just change the concentration in species A with respect to known parameters, and you know N, Ca, and Ca naught. So that's the end of problem 2. Not too difficult, just use a lot of stuff that you might not have seen in the book. Does everyone have this? Alright, so the final problem deals with a reversible gas phase reaction, so it touches on equilibrium. And you have A reversibly going to B plus C. It's gas phase. It's carried out in a plug flow reactor. It tells you that it's exothermic, and the delta H is negative 40 kilojoules per mole. Heat capacities are 30 and then 15 and 15. So the delta Cp is going to be equal to 0. it gives you the equilibrium constant at 300 degrees Kelvin is equal to 100 moles per liter. So that's everything it gives you for the general problem. Part A then tells you that pure A is fed to the reactor at inlet temperature of 300 Kelvin and the Ca0 initial concentration of 0.1. And it also tells you FA0 is 10 moles per liter, or moles per second, sorry. And it asks you to derive an equation for the equilibrium conversion expressed only as a function of the temperature and known parameters. And then also asks you to calculate the equilibrium conversion at 600 Kelvin and the actual conversion obtained when the temperature is at 600.
Do you not need units on your CPA?
It's joules per mole Kelvin, but the delta CP is 0, so
Oh, sorry.
might still use CPA. Yeah, it's joules per mole Kelvin. So you want equilibrium conversion expressed as known parameters. So you can start calculating epsilon. So your Y0 is pure A, so it's 1. Your delta is going to be, so just 1. It's 2 minus 1. You know, your equilibrium conversion is going to be products over reactants. You can rewrite as the flow rates over the volumetric flow rate. And then all follows pretty general stoichiometry. So you can fill this in. So CB equals CC, and it's just going to be FA0 X over, you know, D0 plus 1 plus times 1 plus X over T minus T0 over T0. Same thing down here. And you can simplify that. So cancel things out. So get KC is equal to that, sorry, and then FA0 over V0 is just CA0. So you can rearrange this finally to your KC of T divided by your CA0 times the temperature change is equal to X squared over 1 minus X squared. from here, you can either plug this into your calculator, solve for x, or you can use quadratic formula. So if you let this be s, then what you'll get is s minus x, that's x squared, equals x squared. Then the general form of equilibrium conversion is going to be kind of messy, but not too bad. So that's going to be your equilibrium conversion formula. And from here, you're going to have to adjust using Van Hoff's formula, your Kc, because it's given at 300 Kelvin, and this problem asks you for conversion at 600 Kelvin. So as for equilibrium and real conversion at 600 Kelvin. So the first thing to do is convert Kc at 300 to Kc at 600.